Foundation models for decision-making agents, part 20. Today I'm going to talk about Sherry Yang and foundation models for simulation agents. I already discussed Sherry's work in the previous episode in a summary of CBPR part 5. I want to dedicate a separate episode just for that because, partly it fits into my foundation models for decision-making agents, but I think it's really crucial. So I just thought about maybe doing a separate episode, and this is the episode. So the idea is the following. Actually, if you want to create a simulation agent, you really have to understand a lot about reality. In fact, this goes back to David Deutsch. If you or Feynman, actually, if you want to understand something, then you better learn how to program it. And if you don't understand how to program it, you probably don't understand it. And whether that programming is software 1.0 or 2.0 or 3.0, it doesn't actually matter, because no matter what, human agency is always important. And when we say understand something, we mean understand, we humans understand. So if we want to understand reality as a robot perceives it, in order to create a reality that the robot can learn in, we need to understand that reality. We need to understand the physics of the reality, the geometry of the reality, or whatever it may be. We have certain ways to understand reality. Goes back to Galileo and physics, and epistemology has taught us that a lot of the reality that we actually perceive is often not really complete, but then it's good enough to do stuff, and we're sort of stuck in this, well, what is reality, and do we really know what's going on? And the answer is, we might, but that's not what matters. What matters is the kind of reality that we need to understand to get stuff done. In other words, to build products and services. So, sorry for this digression, but what I'm trying to say here is that if we want to build a robot that can move in nature and do stuff, we need to understand reality. Whether we simulate it or whether we just let the robot learn in the real world, in both worlds, we need to understand reality to the extent that we need to be able to program the robot to learn from that reality. So not understanding, if I teach my cat C++ and nothing else, she's still not going to be able to build a robot. Like, we have to understand what physics is. We might not have to understand physics, but we have to understand that there's something called physics, which is just a code word for the laws of nature, which is a code word for patterns observable in nature that we humans can take advantage of for intellectual exercises or for engineering practices. We need to know that these things exist. And then we can build machines that learn from nature in how to move around. The language of robotics is movement. I would say yes, but with a caveat. And now let's introduce Sherry Yang here. What she's saying is that, first, there is a couple of things that robots need to do when they move around in reality. And that is, they need to see or perceive, they need to predict, and then they need to plan. So the three P's of robotics: perception, prediction, planning, PPP, the 3 P's of robotics. And her idea, which goes back to end-to-end learning, we discussed UniAD in the previous episode, but Sherry's idea is that we can have an end-to-end learned robot that is trained with data, and the crucial thing is the data has to be within those 3 domains. So vision and motion and geometry and physics. We need the data. We don't have to teach the robot the laws of physics, but the robot needs to understand that when it holds an apple, that it has to exert a certain force to keep that apple from falling down on Earth, and that force is in some way related to what we call gravity. That thing the robot has to know, because otherwise it's not going to exert the force and the apple will fall. Whether we explicitly program this or whether we have it learned from data is actually not so important when it comes to the final product. What matters is simply that it learns from reality. And what Sherry is trying to build is a simulator. So she now not just wants to learn from reality, she wants to learn reality. There's two advantages to that. One, learning reality just gives you a leg up because now you actually understand reality. And second, you can potentially use that for training in simulation. Why is training in simulation so powerful? This goes to the episode just before the last one, which is parallelism. Parallelism is all we need. We've introduced that phrase 2 episodes ago. We've discussed the power of NVIDIA and the advantage that NVIDIA has. And we've defined it as really building a platform of parallelisms that enable people to do many things at the same time. And this is what drives computation and robotics and AI at a much, much faster pace than Moore's law would predict. It's parallelism. If you can parallelize training, you can learn much faster, and you can also have much bigger models with a lot more data. So what I want to focus on here now is actually the data part. And the data part, that's, in my opinion, in the paper that Sherry was discussing at CVPR, it's sort of in the beginning, introduction, first part, methodology. And very often, I think it gets neglected by researchers because it's either they don't understand it, or even more interestingly, they just don't like the idea of dealing with data. What Sherry is saying is, look, why is it that we have a large language model called GPT that works really well? Well, because we have a lot of text available to train from. Do we have the same with robotics? The answer is no. We have a lot of internet video data, but we don't have the low-level actuator information that is related to the internet video data. In other words, if a robot grasps a ball, we can see that, but we don't know what kind of forces that hand is exerting on the ball. And we don't know the geometry. We can kind of infer the geometry maybe from the video, but even that is difficult because we don't have a 360 view of the actual hand going out, reaching out, grasping, and doing all that kind of stuff. And that's what she's trying to do with the foundation model for simulation agent. She's trying to build a model, feed it the data that is necessary. So from motion to sensory to low-level physics, all that data is combined, and this is crucial. This goes back to UniAD. It's also combined in a way that the headers that are built on top of this, so the perception header, the prediction header, and the planning header, they are all sourcing from the same latent representation of learned features. This is the key. This is the foundation model for embodied decision-making agents. This is what it actually means. And why is the foundation model? Well, because it's like the word says, it's a foundation. On top of this, we can now learn, hopefully, we can learn how to grasp, how to drive, how to do all kinds of stuff. I've already said the biggest takeaway for me personally at CVPR was the idea of transfer learning between driving and grasping and other robotics tasks. And the reason transfer learning works in principle is because it seems like there is navigation at the core of all these tasks. This is a conjecture. This is not 100% proven. However, we believe that that is probably the source of the upside here that we have as robotics researchers if we put all kinds of different data from different domains and tokenize this data and then run it in conjunction in one model. So we learn the grasping and the driving, and we learn vision and prediction. All of this is in one latent representation. And on top of that, we have the headers, which then use self-attention and cross-attention, self-attention being how the particular tokens relate to all the other tokens in the training set, and then the cross-attention, how the input tokens relate to the output tokens. So we sort of learn, like I discussed in the previous episode, this is just a very general form of a state-space model. which goes through all potential states, or at least almost relevant states that particular tokens can have, and finds relationships between the states of the input data and also the cross-attention, the input and the output data. So once we have this gigantic matrix with a multidimensional representation of the real world, we can then use that to learn intelligent behavior of embodied decision-making agents. This is roughly the idea. It's very similar to large language models. The idea is, again, that we have a compressed representation of reality, which is expressed in latent form, in strings, in tokens. We have token per dollar as the metric which drives everything, which is how much more tokens can be produced per dollar. The more, the better. Because in the end, everything is about economics, right? We could have a supercomputer that uses half the world's resources and probably learn how to drive, but that would be pretty uneconomic in many other ways. So we have to optimize token per dollar. And once we optimize token per dollar, we then can and drive that notion up. So more tokens per dollar, or in other words, we have some sort of derivation of Moore's law as tokens, maybe call it Jensen's law. So we have, I don't know, 3 times more tokens every year at the same dollar or something like that. I don't know what the word, you know what I'm saying here. So let's assume we can drive the token per dollar ratio up at a certain clip, and we then can incorporate the necessary data. And that's key. Again, we need visual perception, we need actuator proprioception. All of these types of informations are necessary. How we get them, that's a whole different episode. But let's assume, first we have to establish that we need this type of data. And I want to finish this episode because I don't want to talk about how to get the data. This is something that people are working on. This is what RTX is mainly trying to achieve, I think, and other such open source type endeavors where we collect robotics data, and in particular high-level and low-level information. But let's take Tesla as an example, and why this is another way to come at the same conclusion, which is Tesla has a massive data advantage. So, number one, Tesla is in the position to collect driving data from an egocentric camera and to solve the perception problem and the prediction problem and the planning problem. And it has access to video data and actuator data simultaneously. So the data comes in both ways, because when you drive the car, you can also access the geometric relationship of the car with the environment, and you have access to the actuator data. In other words, you know what the brakes are doing, you know what the gas is doing, while you're driving through this geometric landscape, while you're observing what's going on. So whether you formulate it in a geometric way, in a proprioceptive way, in a sensory way, you can incorporate all this data, create a foundation model, and then learn. Now, most importantly, and this comes across in the UNIAD data paper, you also need a way to evaluate your models. And this is something that Elon Musk has talked about at length, which is it becomes more and more difficult to evaluate models. How do you know a model A is better than a model B? Tesla has an advantage here, again, because of shadow mode. They can actually run models in A, B, C, D, E, F testing, and you can go all the way down the alphabet. You can have different versions of models tested on different drivers in shadow mode. This is the key. So very low risk, very high reward, and those are the things that make Tesla very unique. So it's not just the access to the driving data set, it's also the ability to test the models. Now, this is becoming more and more difficult, as Musk said, so we want to acknowledge that, but it's still a lot easier for Tesla than for anybody else because they have the infrastructure. So to summarize, the foundation model for embodied decision-making agents, part 20, talks about the simulator. So building a simulator. And we spend most of this episode actually not even talking about simulation. The reason is because we need to understand reality before we build a simulator. And once we build a simulator, we have the problem of the reward function. And I think this warrants a whole separate episode. What we want to talk about here is primarily the need to incorporate all the necessary data into a common representation and have the ability to test models. And those are two things that Tesla can do that all the researchers are also able to do. However, they struggle in particular with the problem of the ground truth. What is good driving or good behavior in general with robotics? Tesla will have that similar problem, of course, with the humanoid robot. What is actually good behavior in a humanoid robot? But with driving, they know, because they have millions of miles of driving, and this is a good approximation for what good driving means. Thank you.